Welcome class to this session. So this is design of steel structures and I'm Engineer Ranjan Argarmi. So today we are going to discuss about compression members. So first, compression members include the column theory. So if we have here a static column, of course when it is loaded, actually by compression, say we have here P, of course the failure mode of that one will be crashing. Ideally, in actual, you should have a substantial loading P in order to crush the steel. While if we have a longer column with the same loading, the failure mode here is buckling. So it is said that if you double the length, the actual capacity of the loading will be reduced 4 times. So in the column theory, we have the Euler's theory, wherein it is proposed that we have a critical buckling load denoted by PCR. The load here is still in the elastic condition. So PCR is given by the expression pi squared EI all over L squared, where E is the modulus of elasticity, I is the moment of inertia along the principal axis, and L is the unbraced length. Recall slenderness ratio SR. Now, slenderness ratio involves radius of gyration, wherein radius of gyration is given by square root of I all over A. Hence, we can say that I is equal to AR squared, and applying the basic formula for the actual load, we have F is equal to P all over A. F here is the stress. So integrating that in the formula will come up with the Euler's critical strength, or this is what we call the elastic critical stress. So this is denoted by F sub E, given by the equation pi squared E all over the square of the slenderness ratio SR. So this is derived by the formula PCR pi squared EI L squared, integrating that I is AR squared and the stress is equal to P all over A. So we note here that the higher the slenderness ratio, the lower the FE, or the Euler's critical stress, and vice versa. So as the column becomes longer and more slender, the load it can carry becomes smaller, and also it buckles easily. Now to illustrate that into the stress and strain diagram, of course the ordinate here will represent our stress, and the horizontal axis will be the strain. Now within the proportional limit, of course we all know that the strength is within the proportional limit. We apply the Young's modulus of elasticity on the slope of that one. So this curve is a representation of the elastic behavior of our member. So with that, it's normalized by a tangent line. Of course, we will be dealing with the yield strength Fy and the tangential modulus of elasticity. So on the transition of the curve, of course, we have here the inelastic buckling, wherein we have FCR is equal to pi squared times E sub t all over slenderness ratio squared. So on this zone, we have the elastic buckling. Now let me emphasize here that in elastic buckling, we have the so-called intermediate column, wherein the failure is a combination of the yielding and crushing. While in the elastic buckling, the mode of failure is purely bending. So this is also expressed in the formula of FCR equal to pi squared E all over the square of the slenderness ratio. Of course, we know that L over R is known as the slenderness ratio. A higher slenderness ratio means a lower critical stress that will cause buckling, while conversely, a lower slenderness ratio results in a higher critical stress but still within the elastic range of the material. That is why on that zone, we have the inelastic buckling, which includes a failure mode of yielding and crushing. So the concept of effective length is given by the three conditions. First, the column is perfectly straight with no initial crookedness. Of course, there are also effects of the transshipment of these materials from the manufacturer up to the construction site. So that will cause crookedness. Okay. Secondly, the load is axial with no eccentricity, and the column is pinned at both ends. So with these three basic assumptions on the Euler's and tangent modulus equation, we need to adjust, or we need to have an adjustment factor for the effective length. So that is given by this diagram, wherein if we have here a different configuration, there will be a theoretical value. For first, we have here a fixed-to-fixed end support of our column. And then we also have here the combined fixed and hinge connection, and then a combined fixed and a roller allowing horizontal displacement on the other side. And we also have the hinge-to-hinge connection on both ends, and the fix to a free end, wherein the free end is freely to displace horizontally and rotation is allowed. And we have also the pin at one end and a roller which allows horizontal displacement. Therefore, the slenderness ratio will now include the K factor. So the Euler's critical stress is also given by this stress and strain diagram. Of course, we will be dealing with the ordinate, stress, and abscissa of the value of the slenderness ratio with the factor K. So FCR here, we note that FCR is flexural buckling stress. So this is our slenderness ratio, with the factor K. Now this is the boundary between the elastic bending and the inelastic buckling. So that is given by the equation 4.71 square root of E all over Fy. And that is actually Cc. So this is the critical slenderness ratio, wherein the curves are approximately tangent. So on that zone, we have here the inelastic buckling and the elastic buckling. As mentioned, inelastic buckling is a combination of the yielding and crushing, while elastic buckling is purely buckling failure mode. So if we have an inelastic buckling, we're going to use a flexural buckling stress equal to 0.658 Fy raised to Fy all over Fe. That is multiplied by Fy. On the other hand, if we have here an elastic buckling, we're going to use a yield strength equal to 0.877 of Fe. Now it should be noted here that KL over R, or K times slenderness ratio, should be only limited to 200. So that is actually the provisions of NSCP 2015 section 505. Slenderness ratio SR limit should not be greater than 200. So in here, we're gonna compare KL over R to that of the CC to determine whether your mode is inelastic buckling or elastic buckling. So the Euler's buckling stress will be given by Fe is equal to pi squared E all over the square of the slenderness ratio. So critical slenderness ratio is given by Cc equal to 4.71 square root of E all over Fy. Now if our KL all over R is less than or equal to Cc, or simply if your Fe is greater than or equal to 0.44 of Fy, that will be classified as intermediate column, or we have here the inelastic buckling mode. So we're going to use a flexural buckling stress equal to 0.658 raised to Fy all over Fe multiplied by Fy. Now if your KL all over R will be greater than Cc, or Fe is less than 0.44 of Fy, that is long column and will be under an elastic buckling. Hence, we're going to use a flexural buckling stress equal to 0.877 of your Fe. So, these are the variables. FCR is flexural buckling stress. Fe is the elastic critical buckling stress. Now, those will be integrated or included with the nominal strength Pn. Of course, we all know that nominal strength is just the product of the area and the yield strength. So, of course, we will be dealing with the yielding, since in here we do not have any fracture assumptions on the members. So basically, the nominal strength Pn is equal to FCR all over Ag. On the previous discussion, Pn is equal to Fyag. So we just replace that Fy by the flexural buckling stress FCR. Again, we will be dealing with the gross area because yielding is always paired with gross area, but not the nominal effective area because again in here we do not have fracture. So of course we're familiar with the LRFD and the ASD reduction factor. So this time phi under compression is 0.9 for LRFD and omega compression is 1.67. So that is also similar to the factors that was used in the tension members. Hence, under LRFD, we can derive the design load equal to phi Pn, while that on the ASD, we can derive PA, which is the quotient of Pn all over omega C. So we have here notes on steel sections used as columns. Column sections with larger R values are more resistant to buckling. So take note, R values, the radius of gyration. So let us compare here three different steel sections. In here we have a flange section with a greater depth and a flange section with almost equal depth on X and Y axis, and then the tube section will be a uniform length on all sides. So here we have the various properties in terms of the area, the radius of gyration along the x-axis, and the radius of gyration along the y-axis. So let us take note here. We also have a minimum radius of gyration in the table that is diagonal instead of Rx and Ry. So notice here that the first section has different values or has a wider range of values, wider difference of values on Rx and Ry, while the second section here, Rx and Ry difference is getting nearer, while on the hollow tubing we have an equal value for Rx and Ry. So let us try to compute the slenderness ratio based on that. Given that we have a 15 length, okay, we just divide that by 1.3 or the lesser value of the radius of gyration. Hence, the critical slenderness ratio will be equal to 138.5 on the second section. Dividing that length by the lesser radius of gyration, 2.54. Now, you might ask why is it that we are going to choose the lesser value of the radius of gyration? Because of course the critical radius of gyration will be the greater value between the two computed slenderness ratio using X and Y axis. Given that, of course, the divisor here is the radius of gyration, of course, we're going to use the lesser value for R. So on the third steel shape, we have L over R will be equal to 41.1. So notice here that on steel tubing, we have the lesser value of the slenderness ratio. So the indication of that is, of course, the better. Because the lesser the L over R or the slenderness ratio, the greater probability that is lesser than your CC. So the most efficient column sections for axial loads are those with almost equal Rx and Ry values. So of course that is a circular pipe. Circular pipe sections and square tubes are the most effective shapes since their radii of gyration about both axes are the same. Circular pipe sections and square tubes are often used as column for light to moderate loads. Wide flange shapes may be preferred despite the structural advantages of closed cross-sectional shapes like tubes and pipes. So the advantage is the wide flange sections can support heavy loads. Okay, note that tube and pipes are only recommended for a loading of light to moderate loading. Wide flange sections also accommodates beam connections because of its configuration. We also have special wide flange sections are specifically manufactured to provide relatively symmetrical columns, okay, wherein Rx and Ry ratio will approach 1 with large load carrying capability. So most of these column sections are generally W8, W10, W12, and W14 sections. It has a depth and flange widths approximately equal. So therefore, somewhat a boxy configuration. In practice, a column may not be pinned at the ends. Why? The column length free to buckle is greatly influenced by its end support conditions. Of course, when we allow strains or rotations as well as displacement, there are bigger chances of buckling. So the load carrying capacity of a column is affected by the end support conditions. So this is the keynote here, wherein there is the straining of the ends of the column with the fixed support will increase the load carrying capacity of a column because, again, a rotation and displacement will certainly affect buckling. So allowing translation as well as rotation at one end of a column generally reduces its load carrying capacity because there is a movement already on the ends if we allow translation and rotation. So for the column failure modes, first, the short columns. So it is classified as short if your slenderness ratio will be less than or equal to 40. So the failure mode on that condition is crushing. Long columns, so the range of the slenderness ratio is from 120 to 200. So the mode of failure here is backlink. So for structural steel columns, it should be noted that this is the limit. Of course, it should not exceed 200 for the slenderness ratio multiplied by K. So for intermediate columns, the range is from 40 up to 120. So the mode of failure is a combination of crushing or yielding and buckling. So let us have sample problems. For this problem, we have A36 hinge at both ends. Rectangular column is 100 by 150 millimeters in cross-section. Letter A, determine the mode of failure of the compression member if its length is 4 meters. Then determine the allowable and design compressive strength in kilonewtons. So here's the cross-section. We have a width of 100 and 150. So as a solution, first, we need to compare KL all over R to that of the CC. So in this case, we investigate the x-axis. Of course, we will be needing the value of the radius of gyration for the x-axis. So that is given by the equation square root of I all over A. So in here, we need to compute for the moment of inertia about the x-axis. So this is Ix. Of course, the base here will be your 100 and the height will be the 150. So we substitute that into our equation. We'll come up with a value of 28,125,000 millimeter raised to 4. So knowing that, we can substitute that one as well as the area 100 by 150. We'll have 43.3. So moving on, the KL all over R of our Y. So of course, we also solve for its radius of gyration along the y-axis. So this time, this is the y-axis. Your base will be 150 and our height will be 100. Applying that into our equation, it will just interchange BH compared to the calculation of Ix. So we can have 12,500,000 millimeter raised to 4. So with this I, of course, we can now compute for the corresponding radius of gyration along the y-axis. And that will be equal to 28.27 millimeters. So applying that on the SR or the slenderness ratio of x and y axis, first we have the x, we have the length of 4 meters or that is 4,000 millimeters. Dividing that by 43.3, we have 92.38. So similarly, for KL all over R of y, we have 138.56. So in this calculation, I and R are still to be determined. Now, if we are dealing with tables, of course, I and R could be predetermined. That is why, again, it is desirable to select an I with a smaller value. Okay? So in this case, Ry prevails. Why? Because it has a larger slenderness ratio. And notice that KL all over R of Y involves the smaller value of I, comparing it to the I of that X. So of course we're going to choose the higher slenderness ratio, that is 138.56. So of course that higher value will be compared to our critical slenderness ratio. We have 4.71 square root of E all over Fy. That is equal to 4.71 square root of 200,000 times all over the yield strength of 248 for a 36 steel shape. So this is equal to 133.6. Now, if we are going to compare that one, obviously, KL all over R is greater than your CC. Hence, that is within the zone of the long column or elastic buckling. So the failure mode is buckling. So that solves our first requirement, letter E. Hence, we would like to check also the limit of KL over R should be less than 200. So since KL all over R is 138.56, that is less than 200, that is okay. So for letter B, we determine the allowable and design compressive strength. When we say allowable, we are referring to ASD, and the design load or the design strength is LRFD. So as a solution, of course, we base our strength parameters on the result, wherein the result is long column. So if it is a long column, we are going to use a buckling strength of 0.877 times the Euler's critical buckling stress. So that is equal to 0.877 times this expression. Of course, you just have to substitute. Now the denominator here is the slenderness ratio, or the largest among or between the x-axis and the y-axis. Of course, that is 138.56. So we can get the Euler's critical buckling stress of 90.16. Now FCR here will be associated with the nominal strength FCR times AG. So 90.16 multiplied by the area 100 by 150, that is 1,352,400 newtons. Now by LRFD, we'll just have to multiply that Pn to your reduction factor, equal to 0.9. Okay, so therefore, the design strength will be equal to 1,217,960 newtons, or that is equal to 1,217.96 kilonewtons. Now, by allowable strength design, we get the allowable load by this formula. It includes omega for yielding, which is equal to 1.67. So we simply multiply our Pn to 0.6 in order to derive our allowable loading. So Pa will be equal to 0.6 times Pn. We have 811,440 newtons. And then that is equal to 811.44 kilonewtons. So those are the allowable and design compressive strength in kilonewton using LRFD and ASD respectively. So problem number 2. Calculate the allowable and design compressive strength of the given W350 by 90 column. So in here, we're going to get the properties from the table, which includes the width of the flange, the depth, the flange thickness, and the web thickness, and then the moment of inertia along X and Y axis, and then finally the area. So this column is actually fixed at one end and hinge at the other end. So it has a length of 4,500 millimeters. So in this configuration, in terms of support, of course, we adopt a theoretical value of K equal to 0.7. So KL all over R along Y. So in here, since we have already the properties, we'll just have to select an axis that has the lesser value of the moment of inertia in order to come up with a larger value of KL all over R. And that is actually acting on the y-axis. So between this, we're going to choose y-axis because that is lesser value. That has a lesser value of I, 44.54 times 10 to the 6 millimeter raised to 4. So we derive Ry is equal to square root of I all over A. So we substitute with the area 11,550 millimeters squared. So we will have 62.09 millimeters. So substituting that further into our slenderness ratio, applying the K value 0.7, we'll have 50.73. Now we do not bother ourselves computing for KL all over R of X again because we have already selected the lesser value of I, in which it is geared towards the result of a larger KL all over R. Now, we compare the KL all over R with your critical slenderness ratio, CC 4.71 square root of E all over Fy. So we just multiply 4.71 by the square root of 200,000 all over Fy of 350. So this is equal to 112.59. Now, comparing these two, of course, we can say that KL all over R is less than CC. Therefore, it will fall under intermediate column, wherein the failure mode is yielding and buckling. So in this case, we are going to use this buckling strength critical equal to 0.658 raised to Fy all over Fe times Fy, wherein the Euler's critical buckling stress is given by that expression. Of course, substituting the KL all over R and E, we have 767.01 megapascals. So knowing that, we can substitute that into the buckling stress to be used. Okay, so we will derive 289.15 megapascals. Hence, for the nominal load, we have FCR times AG. So we have 289.15 times the area of 11,550. We have 3,339,682.5 newtons. Now, by load resistance factor design, you just have to multiply the nominal strength by your phi equal to 0.9. Pu is equal to 0.9 times that value. So therefore, Pu will be equal to 3,005,714 newtons, which is equal to 3,005.71 kilonewtons. By the allowable strength design, again, we'll rely into this formula, wherein omega for yielding is 1.67. Of course, that will have a value of 0.6 times Pn. So therefore, the allowable load is given by 0.6 multiplied by the derived nominal strength, and that would yield to 2,003,809.5 newtons, or simply equal to 2,003.81 kilonewtons. Now these are the values of the design load and the allowable load using LRFD and ASD respectively. Problem number 3. Referring to the figure below, a build-up section that consists of W350 by 90 with two 15mm plates form a box. The section is used as a column that is 12 meters long. The column is assumed to be hinged at both ends and braced at the mid-height of the wick axis. Calculate the design and allowable compressive strength of the column using Fy of 248 megapascal. In here, a special condition wherein W350 by 90 will be combined with 15mm plates. Of course, another condition here is the column is braced at the mid-height of the wick axis. Now, how can we determine the wick axis? So the wick axis lies on the axis parallel to that of the eye with a smaller value. So the major principal axis here would be x-axis, since it has a greater eye of 266 times 10 raised to 6, while the minor axis will be your y, 44.54 times 10 raised to 6 I. So this is the flange 350 by 90. Of course, this will be combined with two 15mm plates. So 15mm is the thickness. Of course, the depth will be equal to the depth of this flange. The depth of this flange is 350. So we start with the x-axis, wherein there will be a combined moment of inertia of the flange and the additional by the plates on both ends. So therefore, I prime x is Ix for the flange plus, of course, we have here a rectangular section. The I for rectangular section is bh cubed all over 12, and we also add here the transfer distance if there will be a transfer distance. So I prime x is equal to, so for xi is 266 times 10 to the 6 we add, okay, the two plates. So base here is 15, height is 350, and then there are two of them. That is why that is multiplied by 2. So next is the value of this one, AD squared, or this is the transfer distance, which is obviously equal to 0. Why? Because from the center of gravity, there is no transfer distance, because there will be no transfer distance along x. It so happened that the centroid of those additional plates coincides with the center of gravity of your W350 by 90, which is at the mid depth. So therefore, we'll just simply calculate that one without considering AD squared, because AD squared is 0. We'll come up with the value of 373.19 times 10 raised to 6 millimeter raised to 4. So Rx is equal to square root of I all over A. Of course, we substitute the values. So on the denominator, take note that we add the two plates, okay, that are attached on both ends of the flange. That is why 11,550 will be combined with that area of 2 by 15 by 350. So by the way, this area is equal to 22,050. So this will be equal to 130.09 millimeters. So therefore, we can now compute for the slenderness ratio along the x-axis. So x-axis here happens to be our major principal axis. So hence we have here 92.24. Now considering the other axis, so this time we are dealing with the y-axis, IY. By the way, we cannot still rely on choosing the lowest I, because in here we have an additional plate that will certainly affect the total moment of inertia of this section. So I prime x is equal to IY plus BH cube for the two rectangular sections of the plates, plus the transfer distance formula AD squared. I prime y therefore is, of course, the I for the flange is 44.54 times 10 to the 6. We add the two plates in rectangular form. So this time our base is 350 and our height is 15. There are two of them, that is why that is multiplied by 2. So for this third term, AD squared, of course this will be our centroid for those outer plates. And this is the axis of consideration, considering the y. And this time we have the transfer distance D, symmetrical on both sides. Therefore, D is equal to 7.5 plus 125. So 7.5 is actually the half of your thickness 15, and then 125 is actually the half of the total width 250 of the flange. So we simply add that one, we come up with a transfer distance of 132.5 millimeters. So we simply add the area. So 15 by 350, there are two of them, multiplied by the transfer distance, that will be squared. So calculating that I prime y, we have 229.08 times 10 raised to 6 millimeter raised to 4. Hence, our radius for variation of y we have square root of I all over A. Substituting the values, we have 101.93. So KL all over R will be computed for Y. Okay, so in here, we use 6,000. Why 6,000? Because there will be a condition in the problem. The column is assumed to be hinged at both ends and braced at the mid-height of the weak axis. And obviously, the weak axis is on the Y. That is why, instead of using 12,000, so at the mid-height of 12,000, so therefore the unbraced length for the Y direction is 6,000 or half of 12,000. Okay. So this is equal to 58.86. So substituting the values 58.86 for Y slenderness ratio, and a while ago we have 92.24. So between the two, of course, we're gonna consider the larger value, 92.24, and this larger value will now be compared to our critical slenderness ratio, 4.71 square root of E all over Fy. Okay, so we just simply substitute the strength parameters. We have 133.76. Now comparing KL all over R to CC, of course, that is obviously less than CC. So if it is less than, that will fall under intermediate column, wherein the failure mode will be a combined yielding and buckling. So intermediate column, of course, that is under inelastic buckling. We're gonna use this formula. FCR is equal to 0.658 Fy all over Fe times Fy. So considering the Euler's buckling, critical buckling stress, so we substitute. Of course, note here that the critical slenderness ratio selected a while ago is the larger one, 92.24. Okay, so therefore, the Euler's buckling stress is 232 megapascals. That will be substituted in the value of the buckling stress to be used in the nominal strength. So that will be equal to 58.54 megapascals. So multiplying FCR to that AG, we derive the nominal strength Pn. So therefore, 158.54 times 22,050 is the area. We have 3,495,827.73 newtons. By the load resistance factor design, we have to multiply your nominal strength by 90%, and that will be equal to 3,495,827.73 times 0.9, that is 3,146.24 kilonewtons. This is the design strength. For the allowable strength, we have to divide your nominal strength by the omega factor of 1.67 for yielding. Of course, 0.6 times the derived Pn. We have 2,097,496.64 Newton, which is also 2,097.5 kilonewton. So this is the allowable strength by allowable strength design. So that's it for today. Thank you, class, for listening, and have a good day, everyone.